Beyond the state variables that have to be tracked throughout the simulation and the control laws, there are the component modes as well. And the component modes are actually what drive the whole simulation and kind of what give it, I would say, a lot of the meaning. And so these are essentially just this is how we tell the simulation whether a component starts out as working or has failed. And more specifically than failed, what sort of behavior it's failed in, right? And so for the valve, as we've already discussed, there's the nominal on, nominal off, right? And then the failed open and failed closed. For the pipe, there's nominal, and of course all of them are going to have nominal. The other modes are failed in a leak and failed clogged. So those are just failure modes of a pipe, right? So the pipe is leaking, which means that, for example, the liquid flow out is less than the liquid flow in, because some of it is being essentially lost to the system. Just to summarize some of the important information during this simulation step of FFIP, the x of t variable is the overall system state, so it keeps track of the system state, which is a composition of the component modes and the state variables on the previous slide. So it's a combination of the state variables, so what the different values are of the state variables, as well as what the modes of the component are. And that's represented with this x of t. Okay, so the last element of FFIP to kind of bring it all together is this functional failure logic, or FFL logic. The FFL logic is a reasoner, so it looks at the information within the system and makes a determination based on that information, and is used to determine the state of the system functions. So again, that means that it's going to look at the information in the system and determine which functions are lost, which are operating nominally, which are degraded, and so it's giving an assessment of each function within the system based on the information it has. So that's what it does, and then the value is that it provides the feedback to designers in order to eliminate the vulnerabilities within the system. So the reasoner uses an FFL to translate the physical system state into the functional failure domain, makes that actual transition, and it uses this x of t that we mentioned on the previous slide. And so the example shown down here represents the different states that a function can be in, whether it's operating, which is the same as nominal, whether it's lost, which is the same as it being failed, so it has no sort of output, or potentially goes across a threshold, or it's degraded, so it's still working to some level, but not as you would expect it to. Let's look specifically at the function failure logic for guide liquid. In this particular case, the guide liquid is implemented by the pipe. In this case, I think it's the inlet pipe. So guide liquid, the functional failure logic has the control signal in, right? Again, so it depends on the level of the tank and whether that is controlling it open or closed. So if the control signal is on, then we can say that if the output of the guide liquid function is 0, then the function is lost. Otherwise, it's operating. So in this particular case, it's one or the other, right? Because if the control signal is on, then the expected output is that there's flow, right? So we would say it's essentially failed or lost if we don't see that. If the control signal is off, and by the way, I'm working my way through this logic here. If the control signal is off, then the if the output is 0, then we would also say that the guide liquid function is lost. Okay, sorry, that I had to stop for just a second and realize I had two of the statements backwards. So this middle section was actually wrong. So if the control signal is off, we expect there to be no flow, right? So the Q out should be 0. So that represents an operating scenario. Otherwise, meaning we do see flow, if that's the case, then it's the function has failed. Okay, and then the other thing we say is the function has failed if there's no signal to it as well. And essentially the text on the far bottom right over here is just an interpretation of the kind of pseudo code that you see here. Another example of a different function is transfer liquid. And in this case, we have input flow and input pressure and output flow and output pressure. The failure logic here is only I'm only representing part of it, so I don't represent the pressure in this particular case. But the failure logic in this case says that if the output flow is less than the input flow, then we're in a situation where it's degraded. If the output flow is 0, then the transfer liquid function is lost. Otherwise, it's operating. So a couple of things to note here. One, it's really important to understand all the potential states that something can be in, right? So that's why the else statement is used. So we say if the output flow is less than the input flow, or if it's 0, then we have a problem. Otherwise, it's good. And so that precludes the option where there could be too much flow, which makes sense because there's not a way for the pipe to get more flow, only to lose it, right? So in this case, that would make sense. It's also good to know that this example relative to the last one used a scenario where the flow was less than, right, as opposed to equal to. So in the previous example, there wasn't any less thans or greater thans. And so that kind of brought up a new scenario where we could say that it was just degraded, but it hadn't been completely lost. So kind of a partial loss in functionality. Now that I've walked through the steps of the method, I'm going to walk through an example scenario in a little bit more detail. So it's still the same system, so I'm not going to be talking about the system models because they're the exact same ones I just presented on. But in this particular case, we're going to be looking at two inserted failures, which are a clogged pipe and outlet valve fails open. So you can look down on this bottom right area and see for the valve, we'll do failed open, and pipe, we'll do failed clogged. So those are just to kind of relate the particular scenario to some of the previous setup that we've done. I just wanted to point out those specifically in the component modes. Okay, in the actual simulation, the times of the inserted failures are in there. So the first one, the inlet pipe is clogged at a T value of 8. And the value of 8 is kind of irrelevant in terms of real time, but it's really time steps. So the inlet valve is clogged at a time value of 8, and because of that, the transfer liquid function fails, okay? And it fails at a time step later because it takes a minute it takes actually a time step for it to realize it within the function, but more or less it's right after, it's instantaneous essentially. So as we progress through time, so we can kind of look along this timeline on the top, we can see that again at 8 seconds pipe clogged, 9 seconds, or sorry, time value of 8 and 9, and then the transfer liquid fails, and there is a design control law, or essentially a procedure that says if there's a failure in the valve or the pipe, then the outlet valve should also be closed, and this is to prevent drying out. And so that's been inserted, and that happens at a time value of 14. So this is a nominal step in the process, right? And so that, if you think about, that's essentially so that the tank doesn't empty itself, right? So it's not intended to be emptied. And as a result, right now, essentially, as a result of the failed input, the output's been turned off, and so the water level is essentially unchanging. And as a result, what we see is that the supply liquid function, which is right here in the middle of the functional model, is what's going to fail next. And the next failure that we insert is at a time value of 20, and that's the outlet valve fails open. Right. So again, this is a kind of a second failure scenario that's being inserted. And of course, having the inlet clogged and having the out fail, the tank in the middle is going to drain. And so as a result of the failed open, the guide liquid function is lost. And actually at this point, then the store and supply liquid have also been failed and lost. And the overall result of this is that the tank dries out, which is one of the failure modes of the system that's, of course, trying to be avoided. What's interesting about this example is, I guess one of the aspects that's interesting about it is the way that the propagation of the failures occurs. So this is obviously a little bit of an interesting example because there's two failures inserted, one on the front side, one on the back side. But what might be expected, and if you think about doing a FMIA or FMICA, and you're going through and you're producing thousands of lines ultimately, the amount of thought that goes into each line of that is going to be limited, of course, right? So it might be very simple to kind of think, given that the pipe on the input is clogged, that it very simply would just kind of logically, that failure propagation would very logically move its way down the system. It would move, to the next component in the line, which would be the tank, and then it would move maybe from the tank to the other pipe. And it may seem that that's kind of the way that it works, but in fact, it's not that way. And see, given this example, that the propagation kind of jumped around a little bit, and it took a while for actually the tank to fail. And it's interesting because the tanks, when I say the tank has failed, it's actually the functions of the tank that have been lost, even though the tank itself is entirely functional, right? So it's, sorry, I shouldn't say it that way. The tank itself is fine. It has no issues physically. There's no leak in the tank or anything like that, but the actual function of the tank, the purpose of it being there, is actually lost, which is somewhat of an interesting result. I'll now provide just one more scenario with, again, the same case study. In this case, it'll be a sensor failure and then essentially an operator error where the operator mistakenly shuts the outlet valve off, closes the outlet valve. So in this case, the first aspect is that the first failure occurs at a time value of 7. It's just a sensor failure. So what's interesting is there's not actually an immediate effect with this. And so the system continues to work nominally. And then at a time value of 8, the operator shuts off the outlet valve. That doesn't mean that the outlet valve itself has failed. It's just it's been put into the wrong state, essentially. But the functionality is because it was put in that state, it's working in that state as it's intended to. So it works nominally. But as a result, this causes the input. Well, there's liquid coming into the tank, so this causes the tank levels to rise. And unfortunately, since the sensor has failed, it can't see and it cannot detect the height value of the liquid, and it results in an overflow situation. So you can see the progression of failures here. The measure level of the tank is the first to fail, as well as these two together in terms of the sensor. And then as a result, even though the inlet valve is actually working just fine, it has no way to get a signal, so the actual functionality is lost. So again, not necessarily the most intuitive way you might think about how this works, but in fact that functionality is lost. Okay, so with the conclusion of that example, I'm going to point out a different document here. So this is going to be a supplemental document that I'll provide with you guys' homework. And this is one that you guys are actually going to be dealing with for the homework assignment. And this is the scenario, and you can look up a lot of this information online, where Toyota had an issue with their accelerator sticking down. And so this particular example here was developed actually for that case. Again, just very basic relative to the actual Toyota completed system, but can kind of show some of the same results. So you can see the functional model here, the configuration flow graph, and then it kind of specifically highlights the accelerator pedal assembly. And then the document actually walks through a description of the behavior models, and in fact gives the actual MATLAB code to be able to do this. And so you can kind of see that. I'm scrolling through quickly, obviously. From the behavior, though, it goes to part 2 and explains what they're calling their FFIP.m file and the code that goes with that. So that's there with an explanation. And then there's a third part, which is the simulation, and again has the actual code here. I will also provide these 3 M files in case you guys are confident in MATLAB and want to get in. You literally save the 3 M files, you go to this file, and you hit run, and it works. So it's very, very straightforward. And I will point out here that these modes are the modes where you can actually choose the failures, the actual failure modes of the system. So to provide an example of that, we can scroll. So again, mode 1 through 6, but we can scroll up to part 1 and look at an example here where, just as an example, for the throttle component, if the mode is 1, it's nominal. If the mode is 2, there's a low throttle position. And if it's 3, there's a high throttle. If it's 4, it's decoupled. And so if we go back down here, here's your throttle component. It's currently set to a value of 1, which is nominal. And actually this case here with a mode value of 3 for the pedal assembly and the rest being 1, this is the scenario where the accelerator gets stuck down. So essentially, as you're trying to drive, you're pushing on the gas pedal, and when you let off, it stays stuck down. That's the scenario that this actually models. It's important to note that the modes are the inputs and the nodes and functions are the output. So again, these are the inputs. The nodes that come out are, which I'll show in just a second, are a description of the output signal and whether they're high or low or right on or there's none at all. And then the functions on whether they are either healthy, lost recoverable, or degraded. And you can see the example here with the stuck pedal where essentially all the outputs, the inputs fixed, the output of the pedal is fixed to 2, but the remaining components are all degraded, which is shown by high signal value of 3. That's what I mean by degraded. And then all of the functions are of 4, which is noted here as degraded. And a real quick on the loss recoverable, that didn't actually show up in the slides earlier, but it's essentially a 4th state which represents if a component doesn't have the opportunity to work, we would call it loss recoverable. So I think about like an example of an emergency brake. If you go to use your emergency brake and it's failed, you only know when you use it. But prior to that, if it has no input, it has no chance to tell you it's failed, essentially, or working. It could be either way. It has really it's not being tested. It's not being demanded in any way. So that's considered to be loss recoverable. So, okay, so I'll send this out with the homework assignment, this document here. Part of the homework assignment is going to ask you essentially to interpret some results from this case study. So it'll be really useful to actually go through and read each of the 3 parts of this case study and kind of understand, how to take these input modes, right? What it means to put an input mode in and what the output results mean, relative to this system. So you guys will see that. All right, thanks.